Industrial ports are one of the few places where green hydrogen does not need to justify its existence through future promises. It works there because the systems that normally resist hydrogen already exist in a compatible form. Ports are not empty sites waiting for a new energy idea. They are dense, energy-intensive environments where electricity, molecules, logistics, regulation, and risk already intersect. Green hydrogen succeeds in these locations not because it is cleaner, but because it fits into an already stressed system and relieves pressure rather than adding complexity. The first reason alignment happens at industrial ports is that ports are natural convergence points for energy infrastructure. High-voltage grid connections already terminate there to serve refineries, chemical plants, terminals, and heavy manufacturing. Pipeline corridors already exist for gases, liquids, and fuels. Cooling water, utilities, control rooms, and emergency systems are already designed for hazardous operations. When a hydrogen electrolyzer is installed at a port, it is not creating a new industrial category. It is connecting into a system that already understands how to manage pressure, risk, and continuous operation. This matters because hydrogen fails fastest where it has to invent infrastructure from scratch. At ports, it inherits infrastructure instead. The second alignment driver is renewable electricity landing geography. Offshore wind, coastal wind, and large coastal solar projects physically land at ports or very near them. This is not a policy choice. It is dictated by geography and grid physics. Power cables from offshore wind farms come ashore at ports because that is where subsea infrastructure, grid substations, and industrial demand already exist. As renewable penetration increases, these landing points experience periods of oversupply, congestion, or curtailment. Electricity that cannot move inland fast enough loses value, sometimes even becoming negatively priced. Green hydrogen changes the equation by absorbing this stranded electricity at the point of landing. Instead of fighting the grid to export every megawatt, electrolyzers convert excess electrons into molecules that stay inside the port system. This conversion is not an abstract benefit. Electricity is the dominant cost driver of green hydrogen. When ports have access to electricity that is cheap, curtailed, or congestion limited, hydrogen production costs collapse relative to inland locations. The same electrolyzer installed at a port and connected to curtailed offshore wind can produce hydrogen at a fundamentally different cost structure than an identical unit connected to a constrained inland grid. This is why port hydrogen projects are not replicable everywhere. The value is location-specific and system-specific, not technology-specific. The third and most decisive factor is that ports already consume hydrogen at scale. Refineries use hydrogen continuously for hydrotreating, desulfurization, and upgrading fuels. Ammonia and fertilizer plants consume hydrogen as a primary feedstock. Chemical plants use hydrogen in synthesis, processing, and intermediates. In most cases, this hydrogen is produced on-site from natural gas or delivered through established industrial gas systems. Green hydrogen does not need to create a market in ports. It replaces an existing one. This is a critical distinction because hydrogen economics collapse when production and demand are separated in time or space. At ports, hydrogen is produced and consumed inside the same industrial fence, often within hundreds of meters. Because demand already exists and is continuous, electrolyzer utilization is naturally high. Utilization is the silent killer of hydrogen economics. An electrolyzer that runs only when a pilot project wants to showcase green credentials produces very expensive hydrogen. An electrolyzer that runs most hours of the year because it feeds an existing industrial process spreads its capital cost over far more kilograms. Ports solve this problem by default. Refineries and chemical plants do not run intermittently. They operate 24 hours a day, 7 days a week because downtime costs millions. When green hydrogen is integrated into these processes, electrolyzers are sized and operated to match real industrial demand, not demonstration targets. Transport is another reason alignment is so strong at ports. Hydrogen is uniquely sensitive to transport costs. Compressing it consumes energy. Liquefying it consumes even more. Trucking it requires specialized equipment and safety measures. Pipelines are capital-intensive and politically difficult to permit. In most locations, these transport layers destroy hydrogen's economics before it reaches the user. Ports eliminate much of this burden because hydrogen does not need to travel far. It moves through short pipelines at controlled pressures within industrial zones that already manage hazardous gases. By removing long-distance transport, ports delete a large fraction of hydrogen's total system cost. This is not a marginal improvement. It is often the difference between a viable project and a stranded asset. Ports also concentrate carbon exposure, which accelerates hydrogen's value proposition. Refineries, chemicals, and fertilizers are among the most carbon-intensive industrial activities. They are also often export-oriented, meaning their products face increasing scrutiny from buyers and regulators. As carbon pricing mechanisms, border adjustments, and buyer requirements tighten, ports feel the pressure first. Green hydrogen allows these industries to remove carbon at the point of production rather than compensating for it later. This turns hydrogen from a sustainability expense into a defensive investment. It protects market access, long-term contracts, and revenue continuity. Boards approve defensive investments more readily than speculative ones, which is why port hydrogen projects advance faster. Permitting and safety alignment is another underappreciated factor. Ports already operate under strict hazardous materials regulations. Emergency response systems, safety buffers, and zoning frameworks are designed for flammable gases, high pressures, and chemical storage. Hydrogen does not introduce a fundamentally new risk category in this context. As a result, permitting timelines are shorter, and community resistance is lower than in greenfield or urban locations. This does not eliminate risk, but it makes it manageable within existing institutional structures. Hydrogen projects that stall for years in public consultation elsewhere often move forward more smoothly in port environments. The combination of these factors creates a compounding effect. Cheap or stranded renewable electricity lowers production cost. Existing hydrogen demand ensures utilization. Minimal transport reduces system losses. Carbon exposure accelerates payback. Established infrastructure and permitting reduce development risk. None of these factors alone guarantee success. Together, they create alignment. This is why industrial ports consistently appear as the first locations where green hydrogen reaches financial close, while inland or speculative projects struggle. It is important to understand that this alignment does not mean hydrogen is universally cheaper than all alternatives. In many port applications, direct electrification still wins for low-temperature heat or simple processes. Hydrogen's value appears where electrification cannot scale, where molecules are required, or where grid constraints limit expansion. Ports concentrate exactly these conditions. They host processes that need molecules, operate at scales that strain grids, and face physical limits to electrification. Hydrogen fits into these gaps rather than competing head-on with electricity everywhere. Another subtle but critical point is that ports are systems under stress. They deal with congestion, land constraints, competing energy flows, and regulatory pressure. Green hydrogen works in stress systems because it converts one type of stress into another form of value. Curtailment stress becomes hydrogen feedstock. Carbon stress becomes compliance relief. Grid congestion becomes behind-the-meter production. Hydrogen fails in relaxed systems where electricity flows freely, carbon is cheap, and infrastructure is abundant. Ports are rarely relaxed systems. This is why attempts to replicate port hydrogen projects inland often fail. Developers copy the technology without copying the system context. They install electrolyzers without cheap power. They plan hydrogen sales without guaranteed demand. They assume pipelines will appear later. The result is underutilized assets and stalled projects. Ports succeed not because they are visionary, but because they are practical. They already contain the pain points hydrogen is good at relieving. From an industrial perspective, the incentive to switch is therefore not ideological, it is operational. Refineries switch because gas price volatility and carbon exposure threaten margins. Chemical plants switch because hydrogen is already a major cost component, and predictability matters more than marginal efficiency gains. Port authorities support hydrogen because it stabilizes energy flows and attracts compliant tenants. Utilities tolerate it because it absorbs excess generation without requiring immediate grid reinforcement. Each actor benefits for a different reason, but the system as a whole becomes more stable. This multi-actor incentive alignment is rare in energy transitions. Most technologies benefit one part of the system while imposing costs on another. Green hydrogen at ports distributes value across the system. It reduces risk for industry, eases congestion for grids, monetizes renewables, and fits within regulatory frameworks. That is why alignment is durable there. It is not dependent on a single subsidy or policy. It emerges from how the system is structured. The final reason alignment persists is that ports are evolutionary, not revolutionary, environments. They are used to incremental upgrades, retrofits, and system integration. Hydrogen can be phased in gradually, starting with partial replacement of gray hydrogen or limited electrolyzer capacity. This reduces execution risk and allows learning without jeopardizing core operations. Inland projects often attempt full-scale transformation in one step, which magnifies risk and deters investment. Ports allow hydrogen to grow organically alongside existing systems. In summary, green hydrogen works in industrial ports because those locations already concentrate cheap renewable electricity, continuous hydrogen demand, existing infrastructure, carbon exposure, and system stress. Hydrogen does not need to invent a market, build a network, or wait for future conditions. It solves problems that already exist today. That is the essence of alignment. Where these conditions are absent, hydrogen remains a promise. Where they converge, it becomes an industrial tool.